PPC cement, as well as Sapaku cement. Then also our gold members, CRISO Southern African Group. Then our silver members, who are shown here, as well as our bronze members as well. Our associate members, who are all listed here as well. And finally, our academic members. If you haven't already got your copy, the Fulton's Concrete Technology book is out. It's a nice thick book, the Concrete Bible, filled with lots of interesting and useful stuff on concrete as well as cement. If you'd like to get a copy, you can get it on the CEMCON-SA website, or you can just drop an email at info@cemcon-sa.org.za, and the price is 990 Rand if you're a member. Then we have in case for those that are not aware, there's the School of Concrete Technology, who offer a whole range of courses and that on concrete and that, and are associated with the Cement and Concrete SA. Here's their website, set.semcom-sa.org.za. And yeah, feel free to contact them if you are looking for any training or courses on concrete or cement. And for those that are joining us today that are not members, we are always looking to expand our membership pool. The more the merrier. So if you are at all interested, please don't hesitate to contact us, or you can just go onto the Cement and Concrete SA website. Then from the Western Cape branch perspective, we just thought we'd just highlight the final event that will be happening at the end of this year to conclude this year, which has gone a lot better than 2020, I can tell you. And to celebrate this, we're having our first real get-together, a physical contact session, which will be a game of bowls. So we're hoping to have quite a good turnout and perhaps get a bit of competitiveness between the different partners. I know Vilja Penetron is going to battle Seeker, so that's going to be quite an intense game. So if you are interested to partake, it's going to be on Thursday, the 2nd of December, and will cost 300 Rand per team, which will consist of 2 people. But we will be sending a flyer for this next week, I think. So watch the space, and there will be opportunities to get involved. So we hope to see you there. Now onto our talk today. Today we've got 2 PhD candidate students who are with the Concrete Materials and Structural Integrity Units at UCT, otherwise called COMSARI. And today we will be having Emmanuel Leo, who will be giving the first talk, which will be on the development of low clinker concrete with the partial replacement of cement with calcined clay and limestone based on selected African raw materials. In terms of education, he got his undergrad BSc degree at the University of Dar es Salaam in Tanzania, and then he came to UCT to complete his master's. And his research focuses on the development of low clinker concrete by partially replacing cement with the addition of calcined clay and limestone. Then the second talk we'll be having today will be given by Ichebadu Amadi, who is also a PhD candidate with COMSARI, and he'll be giving his talk on enhancing the properties of fine recycled aggregate concrete. He obtained his undergrad BSc degree at the University of Nigeria, and then went on to do his master's at Coventry University in the UK. And Iche's research is aimed at contributing towards concrete sustainability and focuses on enhancing the performance of fine recycled aggregate concrete. And with that, I will hand it over to our first speaker, Emmanuel Leo. So Emmanuel, let me just stop sharing my screen. And then, hold on. There we go.
Thank you very much, Nick,
and there we go.
That introduction. So let me try to share my screen. Is that okay?
That's perfect. Thanks, Emmanuel.
Okay. Good afternoon, everyone. So the title of my research work is Development of Working Concrete, Partial Replacement of Cement with Calcined clay and limestone based on selected.
Excuse me, Emmanuel, the
Yes.
audio is very soft. Can you sit forward, please?
Okay, is that fine? Hello?
No, not yet.
Not yet.
Not yet.
I think you must just raise your voice, Emmanuel. Raise your voice.
And I think you must sit closer to your mic.
Yeah, I'm very close to my microphone. I can try to just raise my voice. So my supervisors are Professor Mark Alexander and Professor Hans Bozuze. So here is the outline of my presentation. I'll start with the introduction. So here we learn what is LC3 and why do we need it. Then objectives, scope and limitations. Then I'll show you the selected samples of carbonate clay from South Africa and Tanzania. Then I'll show you the calculation results of the selected samples. Then optimization results aimed at reducing clinker content in the system. Then we'll see some results from CONCRETEFiX, and then lastly conclude. So what is LC3? LC3 stands for limestone calcined clay cement. So it means a mixture of limestone, calcined clay, and cement. In the literature, you'll see most people researching a mixture of 50% clinker, 30% calcined clay, and 50% limestone. And of course, there's also 5% gypsum. But depending on the required performance of the mix, you can even go down to 40% clinker. And you don't need high-grade carbonate clay. A clay with about 40% carbonate content is usually enough. So in general, proper preparations and optimization of these constituent materials is important. Otherwise, you may end up having a system with poorer performance than the conventional systems. So why do we need this system? We all know that the production process of Portland cement generates about 900 kilograms of carbon dioxide per ton of clinker. Fossil fuel combustion is responsible for about 40%, and the decomposition of limestone is responsible for the rest. So in this case, for environmental reasons, assimilation of limestone must be minimized so as to reduce carbon dioxide emissions. Currently, it is estimated that the production of cement contributes about 80% of global anthropogenic carbon dioxide emissions. And about 40% of cement that is produced globally is used to make concrete. Now, according to the United Nations, the proportion of people in Africa living in urban areas is expected to reach 56% by 2050. So that will result in an immense demand for urban infrastructure, such as bridges, housing, and sewage networks. And most of these structures are usually made of concrete, as it's a relatively low-cost construction material. So this will mean more production of cement and therefore more carbon dioxide emissions. Now, the promising option for lowering cost and environmental impact of concrete is through the use of blended cements, which reduce the clinker content in the cement by replacing it with supplementary cementitious material. Now, the most widely used supplementary cementitious materials, slag and fly ash, are limited worldwide, especially in most of African countries. In South Africa, there are large amounts of fly ash generated by burning coal to produce electricity. However, the burning of coal to produce electricity is also another source of carbon dioxide emission. Now, due to the increasing pressure to reduce environmental emissions, in the long term, the availability of fly ash is also in doubt. Also, the Sardana Steel Plant in the Western Cape ceased to operate in 2020, meaning that there is no longer forex slag in that region. So in this case, it is important that we start to think about alternative materials before it's too late. And then number 2 is about the availability of these materials. Now, sources of LC3 raw materials are almost unlimited. This figure here shows the estimated availability of supplementary cementitious materials versus the amount of cement produced globally. It's clear from the figure that we have limited amounts of slag, flash, and all these other materials, but we have huge amounts of limestone and carbonate clay. Number 3 is about energy saving. Now, in this system, energy saving occurs because the calcination temperature of clays is lower than that of clinker by almost 50%, and they're also easy to grind. There's also a strong chemical synergistic effect when all these 3 materials are combined together, but should be in the right proportions and the right sulfate and alkali content. So in general, the increased compressive strength and the penetration resistance of this system is linked to the porosity refinement produced by the pozzolanic reaction and formation of carboaluminate phases. Lastly, studies done in India and Cuba show that it can reduce more than 30% of carbon dioxide emission. And this is because, mainly because the burning of carbonate clays emits only water vapor, unlike limestone, which emits a greater quantity of carbon dioxide during the clinker production. So the main objective of this work was to use a performance-based approach in the development of low clinker concrete while maintaining the required properties of workability, compressive strength, and durability for structural and structural applications. Now, to attain the main objective, the study aimed at optimizing system chemistry and immunology to achieve synergistic effects with all the constituents, optimizing proportions of material to further reduce powder content in concrete, assessing the performance of the selected low clinker mixes in comparison with the recommended concrete mixes for marine concrete structures in South Africa. Now, the cementitious material considered in this study are cement, limestone, and carbonate clay. Cement is CEM2AL 52.5 from Africa. The limestone is cobalt 5 from Ibera carbonate, which has about 97% calcium carbonate, and 2 samples of clay from South Africa, 2 samples of carbonate clay from Tanzania. 2 water binder ratios were considered, 0.4 to represent relatively high performance concrete from marine environment, and 0.55 on selected mixes to represent medium quality concrete, which can be used in most common construction projects. 2 reference mixes were considered. One is with 100% CEM2, abbreviated here as reference 1 or R1. And second mix is with 50% CEM2 replaced by GGBS, and abbreviated here as reference 2 or R2. Supersizer, which is called the Optima 175 from Chrysler, was also used to improve workability. Now, the first task was to identify potential carbonate clay deposits in South Africa and Tanzania, and get samples of clay from these deposits. Now, because of the amount of clay at the deposits, the potential ones in South Africa are Concosphere deposit, abbreviated here as B clay. Then we have Grahamstone deposit, abbreviated here as G clay, and Hopefield deposit, abbreviated as H clay. And we managed to get samples from all these deposits through different suppliers. In Tanzania, we have Pugu Kisarawe deposits, and there we have 2 types of clay: the Pugu hard, abbreviated as PH clay, and Pugu soft, abbreviated as PS clay. Then we have Matamba Makete deposit and Marangale Mufindi deposits. But we managed to get a sample from the Pugu deposit and sample from Handbag cement plant area in Dar es Salaam. Now, this is how the samples of clay looks like. On the left side, you have samples from South Africa, and on the right side, you have samples from Tanzania. Then the second task was to check the suitability of these clays and the optimal calcination temperature. So this involved XRF, XRD, TGA analysis, and also reactivity test. Now this table here shows a summary of XRF, XRD, TGA, and also the calcination temperature. Now basically, a suitable clay is the one with alumina content greater than 18%, alumina to silica ratio greater than 0.3, and the low greater than 7%. But what's most important is the colonate content, which has to be at least 40%. Now, based on these results, we decided to select B clay and H clay from South Africa, and KH and HC clay from Tanzania for further work. Now, something to note here is the equivalent alkalis in the selected clays. You can see the equivalent alkali of the H clay is very high compared to other selected clays. So this will obviously affect the performance of the S3 mixes with H clay. Now this figure here and table down here shows a particle size distribution of the selected clays after grinding. Now here the target was to achieve D50 less than 10 micron and D90 less than 30 micron before calcination. But during calcination, the particles tend to agglomerate. That's why you have this increase of particle size. And then another parameter that we think is important is this PT surface area of the clay. So in this case, the surface area of the clay, which also includes the internal surface area of the clay, was estimated using a Brunner-Emmentaler equation based on the nitrogen gas absorbed on the surface of the clay using an instrument called TriStar. Now, the good thing about this surface area, it also gives you an idea of the internal surface area of the clay, especially if you have similar particle size distribution. Now, it's clear here that HC clay has the highest internal surface area compared to other clays, and H clay has the lowest internal surface area. So in this case, a mix with HC clay would demand more water or more SP as particle size to get a similar capacity. Now the next task was to get optimal proportions of this material. Now here, the compressive strength of mortar was used as the performance for optimization. And S3 mixes with clinker levels between 40 and 70% were obtained using what's called the mixture design 3 factors approach. Now in this approach, the simplex shape is triangle, and it's possible to come up with contour lines within the triangular regions, as you can see here in these diagrams, and be able to estimate proportions that will give best performance. Now, this system requires adjustment of sulfate and alkali content. Sulfate is adjusted due to the filler effect of the added supplementary cementitious materials, in this case, calcined clay and limestone. And to get full benefit of the reaction, both silicate and aluminate phases, adjustment was done by ensuring that the aluminate reaction peaks occurs shortly after the silicate reaction peaks, and between 13 and 18 hours. And that was done using a isothermocalorimeter available in our lab. And alkali content is adjusted to increase the edge strength, but at the same time ensuring that the long-term performance of the mix is not affected. Now, literature suggests a value between 0.6 and 0.8%. In our case, we decided to select 0.7%. Now, with these two adjustments, sulfate and the alkali content in all the mixed proportions, it's only now the amount of clinker, amount of calcined clay and limestone that control the reaction. Now, this figure here shows optimization of results at 28 days. You can also see the required sulfate for each all these mixed proportions. For mixed with B clay to 1.5%, with H clay 2%, because HC clay was only around 1.2%. And the equivalent alkalis were maintained at 0.7% by adding sodium hydroxide, but it was not possible for mixes with H clay because the alkalis in H clay were already high. So what you see inside here the compressive strength results of the S3 mortars relative to the reference mix with 100% cement. Now, from the results, it's clear that for best performance, the lowest clinker factor is 0.55, which is point E, at which the calcined clay factor is 0.35 and limestone factor is 0.1. Now, because high strength does not necessarily mean high durable concrete, we decided to move up and down by 0.1 clinker factor for the concrete work. And the calcined clay and limestone factors, as you can see this box. Now, the next task was to determine fresh and hardened properties of concrete mixes using the selected replacement levels and proportions obtained from the optimization work. Now, initially, a commercial software, which is called LChem Material Mixture Analyzer, EMA, was used to optimize concrete materials. Now, here all mixes were optimized by adjusting the quantity of the materials while maintaining the required proportions of binder and the water binder ratio. The obtained proportions were then adjusted by carrying out trial mixes, and the target was to get a comparable workability with a slump of 100 plus or minus 10 millimeters, and a superprocessor dosage of 1.2, a limit of 1.5%. Now, however, with the HC clay, it was only possible to achieve a slump of 45 millimeters at a speed dosage of 50%. Now, after several trials, we decided to maintain the amount of water at 160 kilogram per meter cubic and the amount of stone at 1,000 kilogram per meter cubic for all the concrete mixes. Now, so today I'll just share with you some of the results that we have so far. Now, maybe here it won't be very easy to remember these abbreviations, but this side you have SC3, and then the following number is the clinker content, and then you have a type of clay in the brackets. So here this is B clay, H clay, PH clay, and HC clay. Now, here we have the compressive strength results of the mixes up to 90 days. Now, this is the case of 0.4 water binder ratio. You can see here at 7 days, although PH clay has low colonite content compared to B clay, but the 55 mix with PH clay has the highest strength, followed by the 55 mix with B clay and the 65 mix with B clay, and then the reference mix are 1. So here it's mainly because the PH clay has high internal surface area than B and H clay, so it absorbs more some of the variable water, therefore reduce the effective water. At 28 days, the 65 mix with B clay is the best, mainly because of the clinker factor and the colonite content, but the 55 mix with B clay and PH clay are also not far from the reference mix R1. At 90 days, all 65 and 55 mixes are close to the reference mixes, except this 55 mix with H clay. And you can also see that at all edges, mixes with H clay have low strength compared to other mixes. And this is mainly because of the low colonite content, high alkalis from the H clay, and also H clay is the lowest internal surface area. Now, talking about the early edge gain of strength of these mixes, you can see that the 3 mixes with 0.55 and 0.6 clinker factor, special 3 mixes with B clay and PH clay, gain strength similar or better than the reference mix R1. So now that indicates that the A3 system is much better because the binders react strongly during the first few days compared to most binary mixes, where the main problem is the slow gain of strength at the air edges. Now again, here is the case of 0.55 water binder ratio. You can see at 7 days, the HC clay, which has low colonite content similar to H clay, but the strength of the 55 mix with HC clay is similar to the 55 mix with B clay and the reference mix. Now this again is because HC clay has high internal surface area than H clay and absorb much of the available water. At 28 and 90 days, the strength of the 55 mix with B clay is close to the reference mix. And I can see the 55 mix with H clay again has the lowest strength at all ages. The yellow line. Now this figure shows the relationship between compressive strength of the F3 mixes with B clay and H clay versus clinker factor versus H. And we have compressive strength of the reference mixes. This side you have reference mix 2, that side you have reference mix 1. Now you can see for the S3 mixes with B clay, from 3 days onward, there is little gain, almost no gain of strength, moving from 0.55 to 0.65 clinker factor. Now this means that in this system, you do not really need the amount of clinker above 55%. Unlike S3 mixes with H clay, where the gain of strength also depends on the clinker factor, at least up to 0.65, 65%. Now here we have a durability index test results. Now this is the case of 0.4 water binder. You can see all mixes have OPI values greater than 10, and substitutivity and porosity less than 10. So here one can conclude that all these mixes are very dense and have high resistance to penetration of deleterious gases such as carbon dioxide. But just looking at the OPI values, it's clear that the S3 mixes are better than the reference mixes. In the case of substitutivity, all mixes are almost similar. Coming to porosity again, the 3 mixes are better than the reference mix 1, but similar to reference mix 2, except this 3 mix with H clay. Now this is the case of 0.55 water binder ratio. Again, here we have the same story. As 3 mixes are better than the reference mix. Then here similar porosity, similar substitutivity, and the porosity similar or better than the reference mix. Now coming to CCI results, here all mixes have values less than 0.75, meaning that they all have excellent resistance to chloride ingress. But just looking at the values, it's clear that the 3 mixes, regardless of the clinker factor, are better than the reference mix 1, and similar to reference mix. And the corresponding porosity results are, as you can see here in this chart. Now here again is the case of 0.55 water binder ratio. All LC3 mixes have values less than 0.75 in the case of CCI. And the reference mix has value between 0.75 and 1. So here in general, it means that the 3 mixes are better than the reference mix in terms of resistance to chloride ingress. Now coming to resistivity, here's the case of 0.4 water binder ratio. There are 3 mixes, especially mixes with B clay and pH clay, have very high resistivity values compared to reference mixes. And you can see 3 mixes with H clay have low values compared to the mixes with B clay and pH clay, but better than the reference mixes. So this in general, it means that the L3 mixes are less permeable than the reference mixes. Now, same story again in the case of 0.55 water binder ratio. This side you have reference mixes, and that's what you can see. Here we only have one reference mix with 100%. So to conclude, L3 system is the promising option for lowering cost and environmental impact of cement. All selected clays are composed mainly of quartz, illite, and kaolinite. From the optimization results, the best proportion is 55% clinker, 35% calcium clay, and 10% limestone. And from the results, it's clear that L3 mixes perform similar or better than the reference mixes. And it's also important to note that apart from the kaolinite content and other minerals present in the clay, factors such as internal surface area, the internal surface area of the clay, also influence strength gain of the system. So from the result, it's clear that these clays are not the same, and it's important that each source be examined. So thank you very much, everyone, for your attention. Back to you, Nick. Thanks.
Thanks very much, Emmanuel. Very nice presentation, very interesting stuff. I think let's open up the floor to some questions. If you have any questions, please feel free to drop them in the chat, and I can read them out to Emmanuel, or otherwise on the Zoom platform, you can, under reactions, you can raise your hand. So we will start taking questions. No questions for Emmanuel?
Hello, Nick.
Hi, Mike.
Hi, thanks. Thanks, Nick. Thanks, Emmanuel, for the presentation. I have a couple of questions, but I will only ask a few. Now, the first thing I want to know is, in your final slide, you indicate that the best proportion was 55% clinker, but you used SEM2. So how do you arrive at this conclusion if you didn't use SEM1?
No, I use SEM2, but SEM2 has
SEM2 has a range of, I think, almost what is it, 80 to 94% of clinker. So
yeah, the SEM2
so
used at about 4% limestone.
At what?
From about 4% limestone, just 4%. So
okay.
Yeah, so it was, when the clinker was about 95%. So, and we also included that in our I mean, we included 4% limestone in the 10% limestone.
Okay.
Okay. Yeah.
Okay. I also saw that if you looked at the H clay, I think in slide number 12, it was calcined at 850 degrees Celsius as opposed to the other ones. Why was this 12? The case? I think so.
Slide number 12.
Yes, I think so.
Say again?
Your H clay was calcined at 850 degrees as opposed to the other one. So why was this the case?
Okay, this clay was, we received, it was already first calcined by the supplier. Got it from Cowling Group. So we received it already calcined from the supplier.
Okay.
So we had to use it directly.
Okay.
But when we tried, because they also give us a small sample from calcined clay, and we also assigned it at 800 when we tried to check the activity. But the activity were similar, almost the same.
Okay. Yeah. Okay, in slide number 18, Emmanuel.
18.
Nick, if I'm taking too much time, you can let me know.
No, that's fine. That's fine.
This one.
Now, can you please tell us? I mean, you say that the porosity values, the lower right-hand side, the porosity values for your LC3s are lower than that of the reference mix, but that's not the case in terms of interpretation. If you look at the water solubility, why is that so?
You mean all the three mixes?
Yeah.
What? Sorry again. Can you ask again?
So the porosity of the reference mix is relatively higher than that of the LC3 mixes.
Yeah.
But on the other hand, the water subtility index for the reference mix is lower than that of the LC3 mixes. How do you combine these two parameters?
If I have to be conservative on answer that question, I'll just rely on the porosity results, because the subtility values, I mean, there are a lot of and put a lot of errors when you do that testing. But generally, just give you an idea how your specimens absorbs water. I mean, the water gets absorbed when you get exposed to, when your specimen is exposed to in water, and it's so I think I'll just generally rely on the porosity results. But
okay, that's a bit risky. I think you need to look at, if I'm not wrong, I think Prof. Alexander is here. There's a paper on, I think Prof. Alexander wrote it, I think a few years ago, probably this year or last year, on interpretation of water sensitivity index and porosity results. I think you need to look at that paper and have a look at, understand the relationship between the two parameters and how to interpret the results comprehensively. Now, if you go to slide number 22, where you talk about resistivity, I'm just interested to know the size of your prism. It looks like a prism. I don't know whether it's a prism or a cylinder.
It's a cylinder.
What is the size of it? The height?
The height is 200.
Or the length? The height is?
200.
So if the height is 200, and for this this Venner probe, the probe spacing is 50. So you have on either edges, you have I think 25 millimeters on either sides.
Yeah, about 50 millimeters. So that's 150 between
No,
the
no.
last. Yeah.
No, you have 25 millimeters on either sides, assuming you place the probe at the longitudinal center. Now, don't you think this brings to question the validity of these results in terms of the edge effect? I don't know whether you've considered this, the edge effect in terms of resistance. The edge effect, yes. Not edge in terms of AGE, the edge in terms of EDG, GE. I cannot differentiate the pronunciation of these two.
So you're saying that there must be an, but if there's an error, then it is maintained throughout testing of all the specimens. So
yeah, but that's a very risky.
I don't know
I understand you. That's a very risky statement to make. That even if there's an error, then it is proper. It's the same in all. Yeah, I think I'm just trying to raise the point that you need to look at that. There are some guidelines in terms of the resistivity measurements using the Venner probe, and somebody might as well say that your results are invalid. Yeah, okay, I think I'll stop there for now.
Yeah, I was just about to jump in, Mike. I was going to say maybe we should. Unfortunately, we're a bit tight for time. So thanks very much for your questions, Mike, and thanks very much, Emmanuel, for your presentation. But I think it's time that we need to move on to the next speaker. So perhaps you guys can continue this chat after the webinar.
No, I'm done. Thanks, Nick.
Okay, thanks, Mike. Okay, Emmanuel, maybe if you just want to stop sharing your screen, and then we can allow the next presenter, Ichibadu Amadi, to then share his screen. And sure, thanks. Iche, are you ready to fire up with the presentation?
Yes, please.
Okay, great. Okay, thanks, Emmanuel, for your talk, and I'm going to hand it over to Iche now. So Iche, we can see your screen nicely, so the floor is yours. Take it away. Thanks.
Okay. Good afternoon, everybody. Sorry, my network is not particularly the best, so I may have to turn off my camera, please. Good afternoon, everyone. My name is Ichibadu Amadi. I'm here to make a presentation on enhancing the properties of fine recycled aggregate concrete. This is an ongoing research that is being supervised by Professors Hans Boyshausen and Mark Alexander. Sorry, is my slide moving?
No, it doesn't look like it.
So it looks like it's frozen.
Just enter.
What?
Just press enter on your screen,
Okay,
on your keyboard.
I've done that.
Nothing.
So let me start sharing again. Is it better now?
Yeah, we can see.
Sorry about that. So here's an outline of my presentation. I'll start with the background, talk about the problem statements and aim and objectives, experimental program, discuss some of the results so far, and then I'll conclude. There is a global shortage of natural aggregates, particularly river sand and pit sand. This is because sand is mined at a rate that is presently exceeds the rate at which sediments are deposited by all the rivers of the world. It is estimated that about 40 to 50 billion tons of sand is extracted from the earth per annum. And most of these, a significant portion of this goes into cement and cementitious materials production, that is concrete and mortar. The demand for concrete and mortar is fueled by urbanization, population growth, and economic growth. And of course, this high demand has come at a huge cost, as this has created some environmental and socioeconomic issues, which include loss of biodiversity, coastal erosion, and in some cases, sand wars. One way of sustainably addressing these issues will be the use of recycled aggregates from concrete component of construction and demolition waste. Some benefits of recycled aggregates include waste reduction, especially as landfills have become scarce, particularly within the Cape Town context. Another benefit is the conservation of natural aggregates, resources, environmental protection, and of course, there's job creation as well. So here's a picture of recycled aggregates. Now, recycled aggregates can be idealized as constituting of virgin aggregate and old adhered cement mortar. Now, the old adhered cement mortar comes from the old concrete that was crushed to produce the recycled aggregates. Now, between the old adhered mortar and the virgin aggregate, there is an interfacial transition zone. And of course, we can also see that the old adhered mortar looks porous and it is less stiff than the aggregate component. So for this reason, recycled aggregates usually have high water absorption, and they are usually less stiff and they're less dense than conventional aggregates or natural aggregates. Now, when this recycled aggregate is used in the production of new concrete or mortar, there's a new cement paste that obviously bonds with the recycled aggregate, and this creates more ITZs. And as we very well know, the existence of multiple ITZs can impact durability as the transport properties of concrete is raised. So the challenge of recycled aggregate is more with fine recycled aggregates than coarse recycled aggregates. This is because the adhered mortar is significantly more in fine recycled aggregates than coarse recycled aggregates. As a matter of fact, the percentage of adhered mortar increases as aggregate sizes reduces. Now, the use of fine recycled aggregates for structural purposes is restricted. This is because it does not meet the strict requirement for structural concrete due to the shortcomings of the ACP. Presently, there is a lack of understanding on how to improve FRA and FRAC properties. Previous studies have focused on the coarse recycled aggregates due to the less ACP content. Now, the challenge here is to effectively reduce the ACP content as well as the porosity of FRA and by so doing, increase the properties and concrete properties of FRA. Now, the aim of this research will be to investigate procedures to enhance properties of FRA for structural application in concrete production as a large-scale replacement for natural sand resources. Here are some objectives of this study. So one would be to improve FRA quality by reducing the overall ACP content through the systematic replacement of FRA particle sizes less than 1.18 with natural sand. Secondly, we want to also reduce the porosity and strengthen FRAC through the use of supplementary cementitious materials, as well as compare the effects of these different supplementary cementitious materials on the concrete properties, to investigate the underlying mechanisms that result in the changes in porosity and microstructure of FRAC and the effect of these changes on FRAC quality. Then we also want to look at how to optimize FRAC performance using different procedures such as mixed design, mixed procedure, and of course, curing. Then finally, we want to also determine the effect of different FRA replacement levels on concrete properties. Now, here are some research questions, but the underlying research question here is that, can a combination of screen aggregates and the use of supplementary cementitious materials produce fine recycled aggregate concrete suitable for structural application? To investigate this, here are some variables and parameters that have been listed for these studies. Now we have two water binder ratios, that is 0.45 and 0.55. These water binder ratios represent typical water binder ratios used for structural concrete application. Of course, I've mentioned two FRA sizes. So the screened one is listed as FRA1 and the second one is FRA2. Then we also want to look at, we're also looking at three different supplementary cementitious materials, namely fly ash, GGBS, and limestone calcined clay, which my colleague just talked about. But for the purpose of this presentation, we shall be focusing on fly ash and GGBS. And the fly ash and GGBS will be used at 30% and 50% replacement levels, respectively. Of course, these are adopted from industry replacement levels. Then, of course, fine aggregate replacement levels will be investigating 0, 25%, and 50%. Here is a flowchart of this research. Just for emphasis, where for Series A mixes, Series A and Series C mixes will have screened aggregates, while Series B and Series D mixes will have unscreened aggregates. That is everything less than 4.75 millimeters. Now, for the purpose of this presentation, we shall be limiting our discussions to general materials characterization. We shall also be talking about the compressive strength and elastic modulus, just to as representation of the mechanical properties. Then for durability properties, we shall be looking at the 3D test, which is the OPI, the CCI, and the WSI. So these are my recycled aggregate materials. The slab for this, this is the parent concrete that was obviously crushed for this work. So the parent concrete comes from culvert slabs that were used as wing walls and culverts for a road project on the N2. These concrete slabs were first cored to obtain compressive strength. You can see the coring there. And some of them were tested, and these are just a representation of the average strengths. So we can see that the strengths typically vary between 37 megapascals and 75 megapascals. Here is the crushing facility that was gracious enough to process our materials. And this is CDL Services located in Philippi, here in Cape Town. So, but before crushing, the entire production line was cleaned so that to avoid contamination of my samples or my materials. This is what my materials look like after crushing. And of course, after processing, after sieving, these are the two fine recycled aggregate samples that were used. Of course, our materials had to also be characterized by grading. And here is a look at all the fine aggregates that were used, both natural and recycled aggregates. And of course, this is the coarse aggregate, which is the natural coarse aggregate, the Greywacke stones. Here is a sieve analysis of the blended recycled aggregates, fine aggregates. And this we are checked against the ASTM 33 grading limits. And we can see that materials generally fit in within the ASTM limits. We also checked them against the grading limits that were stipulated in Fulton's textbook. It is observed that the aggregates do not entirely fit in here. This is because the Fulton limit is narrower and has a finer grading than the ASTM limits. Here are some properties of aggregates measured in the lab: fineness modulus, moisture content, and all of that. Some of these were used, of course, for the mix design. And for our binders, we did some basic characterization like particle size analysis, and we can see that all of our binders do not exceed 51 microns for the D90 sizes. And of course, our PET surface area is given there. Here's a representation, a graphical representation of what our sieves, our binder sizes look like. So for mixing, the mixing procedure adopted for this study is a modified version of the two-stage mixing approach developed by Tam et al. So the procedure basically involves pre-mixing aggregates in water and pozzolanic slurry to provide more interaction between the recycled aggregates and the binder. Studies have shown that this procedure enhances pore filling and increases pozzolanic reaction. Also, premixing allows fine recycled aggregates to take up moisture without getting to saturation within a few minutes. Literature has shown that some 60 to 70% degree of saturation is required for optimum recycled aggregates concrete performance. So, and for our mixes, we have also used super plasticizers to achieve our design workability, which was fixed at 75 plus or minus 25 millimeters. The SP dosage is kept at minimum to limit any influence of SP. Also, no additional water or water reduction was carried out during this mixing. So here, just a quick look at some of our results. Here's the compressive strength result. So results of the compressive strength basically show that for our screened FRA concrete, that at 0.5, it can be seen that the strength decreases as FRA content reduces. There's this general trend here. Of course, this can be attributed to the different replacement levels of FRA. So this can be attributed to the adhered cement paste that is present in the FRA matrix. But this trend obviously is not the same with 0.45 water binder ratio. This could be due to the water. This could be due to the high absorption rate of fine recycled aggregates, obviously, which may have absorbed some of the mixing water, thereby decreasing the water cement ratio within the binder matrix, and therefore giving rise to higher strength. And you can see that from the result that the on-screen mixes like the D25P and the D50P, which obviously has high FRA absorption, gave us good strength when you compare them to their corresponding mixes. Now, for the mixes with fly ash, it can be seen that it is at 3 days and 28 days strength, fly ash mixes give less strength than their corresponding mixes without fly ash. But after 6 months, the strength of fly ash mixes increased steeply higher than their corresponding mix. This is indicative that fly ash require more curing time to hydrate. The increase in strength is more pronounced in unscreened FRA mixes, which may indicate more pozzolanic reaction between the calcium hydroxide reserve of fly ash and the silica present in fly ash. So a similar trend was observed when we used GGBS. Now for elastic modulus, we can see that the most of the results we have here are for 28 days mixes. Generally, elastic modulus is largely dependent on aggregate stiffness and cement paste content. Therefore, an increase in FRA content results to a decrease in elastic modulus. Also, screened FRA mixes having less adhered cement paste and more stiffness show a higher elastic modulus than their corresponding unscreened mixes. Here are the screen mixes, here are the unscreened mixes, and you can see that. So a similar trend is observed for fly ash and GGBS mixes. For durability properties, we shall use the 3DI test as we have mentioned a while ago, the OPI, CCI, and WSI. As a guide, here are some values that give an indication of concrete quality for these tests. Now, the OPI values for all the concrete mixes are above 10. So this indicates that the concrete is of excellent quality on the basis of OPI. We can see that the OPI values reduce as FRA content increases. You can see that trend. This indicates that porosity and penetrability of concrete reduces with increasing FRA content. So on addition of fly ash, the microstructure of the concrete mix is improved. The improvement is quite significant over a prolonged curing period, as seen from the steepness of the graph, from 28 days to 180 days. This indicates that fly ash concrete may require extended curing. Whereas there's an improvement in the microstructure of GGBS, however, this increase may not be as significant as that of the fly ash mixes, particularly over a longer curing period. For CCI results, we can see that the concrete quality, of course, lie between good to excellent, particularly for the 0.45 mixes. Of course, this is due to their low water content and therefore denser microstructure. On addition of fly ash, results improved significantly, especially over a prolonged curing period. For GGBS mixes, the CCI values improved significantly at 28 days. At 28 days, the CCI values was quite improved. Of course, this can be attributed to the good chloride binding ability of GGBS. For WSI results, we can see that all the concretes fall within good to excellent quality concrete, particularly the 0.45 mixes. Of course, we can attribute that to the denser structure, the denser microstructure, and less porosity of these mixes. Now, results also show that prolonged curing is beneficial to the 0.55 mixes. Results also show that prolonged curing is beneficial to the 0.55 mixes, as we can see a decline in the subtivity values from 28 days to 180 days of curing. This can be attributed to a better microstructural development over a longer curing period. Now, this is a graph that contains all of our mixes, including GGBS and fly ash. And from this graph, we can see that at 50% FRA content, the concrete mixes show better subtivity values. This is quite interesting, as it does not agree with very well with literature, because literature tells us that it is expected that concrete with a high FRA content will increase porosity and its interconnectedness, and therefore more capillary and water subtivity. However, this is not the case here. To gain a better understanding of these results, I am presently looking at studies by Mo, Bakari, and Prof. Mark Alexander, 2021, a paper where they actually stated that from their studies that WSI results must be analyzed alongside the porosity values obtained from the test. And it is on this note, I want to conclude with the following remarks: that based on primary results of this study, the use of FRA for structural concrete application is feasible. The properties of FRA concrete can be enhanced by using appropriate techniques. However, more work is needed to fully characterize FRA as well as the mechanism of enhancing FRA concrete. And thank you.
Thanks very much, Mr. Chair, for that talk. A lot of data and testing seems to have gone into your research so far. So yeah, it's quite a lot of data to sift through. I think let's open up the time for questions. I think we can only have enough time for maybe 1 or 2 questions. So let's open up the floor. Mike, you have a question?
Yes, please, Nick. Thanks. And thanks, Iche, for your good presentation.
Thank you, Prof.
Yeah. One of your, I think, objectives or aims was, can you please go to that slide? I remember well. For the previous slide, please. Yeah. So based on this aim and based on what you've done or the results that you found and conclusions you've arrived at, can you please comment on the reproducibility of using FRA the way you used this in practice?
Okay, Prof. The reproducibility of this material. One thing we know about recycled aggregates generally, particularly fine recycled aggregates, is the variability in quality. And so it is important that we characterize these materials adequately. A lot of characterization work is ongoing. Of course, I can't represent everything in this presentation. And it is based on that we can start talking about reproducibility and you know, that's my own thinking.
Okay, thank you. That's all from me, Nick. Thanks.
Thanks, Mike. Does anyone else have any questions that they would like to ask Iche? Okay, there's no questions in the chat. So we're just about nearly about to hit 4:05, so we've actually gone a little bit over time that we've allowed for. So I think that's enough time for questions then. Iche, thanks very much for your presentation and that. And thanks again to those for attending our talk today. For this CONCRETEFiX seminar, and also thanks to Emmanuel for chatting, for giving us his talk as well. Hanley, you mentioned to me something about regarding CPD points and that. Do you maybe want to step in here?
Yes, thanks, Nick. Just a reminder that anybody who's in line for CPD points, make sure that Natasha has got your details. If you haven't RSVP'd to her, make sure to send her a mail afterwards so she can record it and ensure that you get your CPD points for this. Thank you, Nicholas, and thank you to the Western Cape branch for another good CONCRETEFiX.
Yes, thanks, Hanley. And thanks all for attending. We hope to see you at the end of year function later this year. So yeah. Okay, thanks very much, everyone.
Thank you. Bye-bye.
Goodbye.